Good afternoon, everyone. Thank you for coming to the talk. My name is Logan Beaver. I'm a PhD candidate at the University of Delaware. Today I'm going to be showing you some of our collaborative work on an optimal control approach to flocking. So when I talk about flocking, what I'm really talking about in particular with small birds is this idea of cluster flocking, forming this large sort of aggregate. There's this large scale sort of pattern that emerges from these interactions between the individuals. This also includes the herding of land animals and schooling of fish. It's basically any of these large aggregate behaviors that you can see. It's totally decentralized. There's not some central controller in there governing each of the animals, telling them where to go or what to do. And yet we still get this really interesting large-scale pattern emerging purely from these interactions. So we're going to seek to solve this in an optimal control framework so that the agents are minimizing their energy consumption, which is particularly important in these sort of robot swarm flocking applications. So I'm going to go through just a little bit of the motivation and literature. I'll show you how we formulate the problem as an optimal control energy minimization problem. I'll talk about how we generate the trajectories, both the unconstrained and constrained solution. I'll present some quick simulation results and then draw concluding remarks and talk a little bit about future directions of research. So our objective here is to design an optimal control problem such that the solution to this problem is a controller that induces cluster flocking. The way we're going to do this is sort of the classic method of using Reynolds flocking rules, and we're going to try and embed that in our optimal control framework. We're going to include flock centering, where you move towards your neighbors. We're going to include velocity matching, where you match the velocity of your neighbors, and collision avoidance, where you don't bump into your neighbors. These are the three big rules that Reynolds came up with originally that has been shown to sort of give this type of desired behavior. Here's a snapshot of the literature. As you can see, there's a lot of work published, both in terms of Reynolds flocking, cluster flocking, and even flocking and optimization and MPC approaches to flocking. So this is just a little bit of the related work to what we're presenting here today. The first two assumptions we're going to make about this system here, one is we're going to have no external disturbances or obstacles, and two, we're not going to have any errors or delays in our agent's communication or sensing. This sort of gives us a pure deterministic problem to work with. These assumptions may be application dependent, so depending on your application, you may need to relax them using robust control or maybe a stochastic optimization techniques. Our third assumption is to sort of simplify the analysis. You'll see where this comes into play later on in the presentation. The idea here is the flock is sort of low density, so one agent can only ever come into contact with one other agent at any given time, so you can't have these kind of chains of agents, or you can't have these big aggregates of agents that are all in contact with each other. This isn't required in general to solve the problem, but it does significantly simplify the analysis, as you'll see. So our system here is going to be a swarm of n agents. We're going to index them by the set A for agent. Each of the agents follow double integrator dynamics, so we're directly controlling the acceleration. And all the agents are in R2, so their state is just this stack vector in R4. For each agent, we want to find the control input that will minimize our energy consumption, given by the integral on the right-hand side of the objective, which is the L2 norm of acceleration. The idea here is bigger acceleration magnitude generally correlates to larger energy consumption. And then we have this endpoint cost phi I, and that's going to actually be our sort of soft constraint to control our flocking behavior. Now, the constraints we're going to impose, we have our dynamics and initial conditions. We're also going to impose the safety constraint, so we can come within at most a distance d of any other agent. And this is some positive real number. So basically each agent is a disk of radius d, and they're not allowed to overlap. And in this case, this phi I is sort of this emergence function. So we have three different terms in it. The first is phi d, which is our migration direction. So we can select some direction, northeast, south, northwest, and it will penalize any agent that deviates from that distance or from that direction, that velocity. The second is our velocity matching. So we look at the velocity of all of the agents around us. We're going to average it and then penalize agent I for deviating from that. And then the third one is the flock centering component. So we're going to take the distance between us and all of our neighbors, compare each of those distances to the desired distance, and then penalize it by however much it deviates. One of the sort of advantages of modeling this as an endpoint constraint as opposed to maybe a hard constraint or an integral constraint is that while we're doing the optimal control approach, we only need to consider phi in our boundary conditions and not necessarily in our trajectory. Unfortunately, we don't have time to go through that process, but it's thoroughly explained in the paper if you're interested in seeing more about that. So what we're going to go through next is how we actually generate these trajectories. So we have our initial and final boundary conditions from the optimal control problem. Now what we need to do is look at every possible constraint that can become active, including pairs of constraints that may become active. And these are going to give us sort of these optimal motion primitives. So once we've generated these optimal motion primitives, we then have to use some optimality conditions to piece them together. That will give us a piecewise function that is our energy minimizing control. So here, I'm just going to go through the unconstrained solution a little bit quickly because it's not, kind of the focus of the paper. So we're going to write the Hamiltonian. We have our energy cost as the first term. Then the second and third term, we have the time derivative of position and time derivative of velocity dotted with these influence functions. You can sort of think of them as like equality Lagrange multipliers that ensure we're following our dynamics. They're sort of analogous to that. Then we're going to apply the Euler-Lagrange equations directly to the Hamiltonian. So you can see here that the optimal control input is equal to the negative of the velocity influence function. Taking the other derivatives, we can actually just calculate directly. The optimal control input must be linear for an unconstrained agent moving under the L2 norm of acceleration as its cost, where these constants A and B are just constants of integration that are going to be filled in by whatever our boundary conditions are. The constraint solution is a little bit more involved. So the first thing we're going to do is we're going to take that safety constraint and we're going to write it as a dot product. You may have noticed that I use the equivalent squared form in this case, and this is to make the next step just kind of easier to follow. So we're going to take time derivatives until the control input appears. So we have this first term of n as our original constraint. The second term of n is its first derivative, and this third term is the second derivative, where the control input ui lives inside of this s double dot. These first two terms are our tangency conditions. The idea is that the first one has to be satisfied always, and in order for the agent to remain on the trajectory, the second and third terms must always be satisfied, because the constraint must be equal to 0 the entire time that we're on the trajectory. So the first two are sort of like identities that we can use to help simplify the problem. We know those are always true. And the third term is going to be what is appended to the Hamiltonian. So the constraint Hamiltonian is this. We take the exact same Hamiltonian as before, but we're going to append this Lagrange multiplier mu multiplied by the constraint. You can think of this as an inequality Lagrange multiplier. So this thing must always be non-negative because it's an inequality constraint. And if we neglected our third assumption, then in order to guarantee safety, we would really need n-1 of these mu's. So we would need a mu j for every other agent j. And so we may have 2, 3, 4, 5 of these mu's that are all appearing simultaneously, depending, which combinations of constraints become active. So this is really the reason for that constraint, is right here. So now we can apply the Euler-Lagrange equations. We get something that looks similar to the unconstrained case, but now we have these extra mu, s, s dot, and s double dot terms. And this is a system of nonlinear ordinary differential equations. So the idea here is any ui that is energy optimal, ui star, is going to satisfy the system of equations. So this is sort of a quick sketch of how we get from the system of equations and try to simplify it down. The first thing we can do is we can assume s dot is not equal to 0. If we assume that, so the agents have some relative orbital speed, we know that by the tangency conditions, s dotted with s dot must be equal to 0. And so we can actually construct this orthonormal polar basis. So we have this radial component that is s, our separating distance, divided by d, which is the fixed diameter of the agents. And then we have the angular component, which is just our radial velocity divided by its magnitude. So these are orthogonal from the tangency conditions, and they're normal because we've just divided them by their length. So this is an orthonormal basis that we can then project the identity Sij double dot equals uj minus ui. We can project that onto it. we know what S double dot dotted with S is from the tangency conditions, and we can sort of do a trick with integration by parts to calculate S double dot dotted with S dot, and this will actually give us a different system of equations that are functions of, position and velocity, and we can take derivatives, substitute until we eventually get two ODEs, which are in terms of our relative speed A, our influence function or inequality Lagrange multiplier mu, and our fixed distance D. So these are the equations here. This is third order in our orbital speed A, second order in mu. There's a multiplication between them, right? There's an A to the fourth. So this is a really hard system of equations to solve. And even if you sort of take a steady state solution where A and mu are constant, that also gives you something that's just not a solution in this case. So, you can simplify it a little bit more, but there's not really a closed form to this that'll be helpful. So the other thing we can look at is coming up with a reigning optimal solution, right? Since we know that the sort of general solution must satisfy that ODE, we don't know the solution to that. We can instead look at the case where this relative orbital speed is 0. This means we no longer have a radial component from that previous analysis, but we know the agents must satisfy the tangency conditions. So if the interval is length 0, that means the agents must just come together and separate. So we can use the sort of jump conditions at that point and continuity in the state to sort of piece that together and optimally determine what the state is at that instant. If the interval that the agents are in contact is over a non-zero length of time, then we know that AIT equals 0, or AIJT equals 0, means that VI equals VJ. That means the agents will come together, and then they'll exactly match their velocities, and they'll stick and move together. So this is sort of our reigning optimal solution. If we impose AIJ equals 0, then this is going to be the energy optimal solution. And it's, sort of the best we can do. Here's a simulation that's sort of showing off this flocking behavior. You can see the agents start with sort of a random orientation and velocity in the lower left. They're being given a desired velocity command to move to the northeast, and you can see the agents sort of first prioritize moving into this sort of flexible formation, then while they're doing their velocity alignment, then they start to do the desired velocity direction while sort of maintaining the alignment. Because they're just trying to retain this fixed distance, the formation is flexible, it's able to move, and so it's exactly the flocking behavior that we were hoping to see by imposing this is indeed emerging from this control law. And we have a couple of other simulations in the paper if you would like to see more about that as well. So finally, sort of in summary of what we've done, we presented an optimal control approach that yields this decentralized flocking behavior. The behavior is totally parameterized by this function phi that's evaluated at your endpoint. We've called this sort of the emergence function. We've exchanged this optimal control problem into an ODE and then shown one of the reigning optimal, so far the reigning optimal solution to it. Basically the best solution so far. Some directions for future work. Kind of the most obvious next step is including obstacle avoidance as another constraint. So you now have 3 motion primitives, or maybe 4 motion primitives if obstacle avoidance and safety are active simultaneously. Another direction we've been sort of looking is applying this in a constraint-driven sort of framework where you bring this emergence function down as a series of equations. We've seen some really interesting work that's sort of taking this approach. And then the final sort of direction of future work is validating this experimentally inside of our testbed, the University of Delaware's scaled smart city, to see how accurate it is to sort of have those first 2 assumptions about having perfect information and no errors or delays or noise. So thank you very much for your attention, and I think we have a few minutes left to take questions. Thank you.